Mathematics in cryptography includes algebra, arithmetic, number theory, geometry, topology, and probability. And in this session, I will discuss mostly about algebra. We start with this protocol of sending a suitcase. Let's say in the suitcase, maybe there are some very classified files, and Alice wants to send, so assume Alice has a suitcase and a lock with the key. She wants to send the suitcase to Bob into a secure way so that nobody can see the content of the suitcase. And Bob also has a lock and the corresponding key, but they are not compatible with Alice's ones. So how we send the suitcase? First, Alice closed the suitcase with her lock and send it to Bob. And then Bob put his own lock and send back to Alice the suitcase with two locks. And then Alice removed her lock and sent back to the suitcase to Bob. And finally, Bob can open the suitcase with his key. And we will see later on the mathematical translation of this protocol of the suitcase. And let's start with some short history. So cryptography started with Julius Caesar, where he replaced each letter by another one in the same order. For instance, if ABC until Z here, we shift to D, E, F until C, and then we can have cryptography become something that we can pronounce. And there are more sophisticated examples use any permutation. And then in 1883, so any secure enciphering method is supposed to be known by the enemy, so the security depends on the choice of the key. And then in 1917, we can see that to get the original message and then give the key and then message sent. So this is like we add the original key with the key, original message with the key, and we send the message. Or we can have the message sent with the key and get the original message. So in 1950, Claude Shannon proves that the only secure secret key system are those with a key with at least as long as the message to be sent. So in order to have a secure message, we also need a key that the same length as the message. And we also have seen that Alan Turing deciphering coded message. But then nowadays, now we are going to 1978. The method RSA by Rivest, Shamir, and Adelman. And they invent the method for obtaining digital signature and public key crypto system. So here they use public key for the encryption, and then become ciphertext, and for the decryption they use private key. And in the protocol of sending of suitcase, so the real, say we want to send 111, and then we put the Alice key, which is 7, and this is a public key. We send it to Bob, and Bob put his key, which is 3. And Alice opened his key, and then Bob opened it, and finally, so we have this 111 power 7 is 871 modulo 1000, and then we power with 3, we power with 43, we power with 67, and finally we get our message. So in the public key and private key scheme, so this 7 is the public key and 67 is the private key. But then the current trends in cryptography, if we compute modulo n, means we work with multiplicative group of integer modulo n. And specific attack have been developed, hence a group of large size n is required. And we wish to replace the group with another one, in which is easy to compute, but where the discrete logarithm is hard to solve. And for smart cards, cell phones, a small mathematical object is needed. And a candidate is an elliptic curve over a finite field. And the use of elliptic curve started in 1985. Maybe some of you has not born yet. So by Koblitz and Miller independently suggested the use of elliptic curve in the development of the new type of public key cipher. What is an elliptic curve? So an elliptic curve equation is an equation is in this form: y square equal x cubed plus ax plus b. That's for f in characteristic p which is not 2 or 3. And for f of characteristic 2 is in the form y square plus xy equal x cubed plus ax squared plus b. So let's see, this is an example of an elliptic curve over real. Y square equal x cubed minus x. Another example of elliptic curve, y square equal x cubed minus half x plus half. And this is another example of elliptic curve. But our elliptic curve will be like this, because we are working with finite field. For example, for GF23 or Z23 or F23, the elliptic curve equation still look like the same like the real one. Well, this is also real, but not really real. Okay, no, I'm confused how to say it. I mean, you get these points which are discontinuous, but we still call it a curve. And so this is our elliptic curve, y square equal x cubed plus x plus 1, and where the x is from 0 to 22, and the y also from 0 to 22. And you can see it is symmetric here. And we also can define the addition on that elliptic curve. But let me give you the picture for the real one. Okay, you know what I mean by real. Okay, so I wish to use this, but okay, then let me just use my finger. Okay, so this is point P and another point Q, and we make the line from P to Q, and then we get the third point here, and then we reflect, and this is the point P plus Q. And how if how to compute P plus P or 2P? So this is done by drawing a tangent line. Do I have it here? Yes. Drawing a tangent line on this point P, And you get the second point, you reflect, and that's the point 2p. And for you who teach calculus, this could be an interesting problem for your students, how to find the tangent line and then the intersection and then make it the reflection and so on. And you can even play, how about 3p? So 3p is p plus 2p, and then you can play with this and with, let's see, sorry, p plus 2p, you get the p, and then 2p, you get the line, and then you get the third point, and you reflect, and you get 3p, which is here. And you can play, if you're bored with what I'm saying, you can try 4p, 5p, and so on until lunchtime. But finally, we can do this by computer. We can have, say, if p coordinate is x1, y1, and p2, p2 is x2, y2, and then we can compute p3, which is, p1 plus p2 with coordinate x3, y3 can be computed with this formula. Lambda square plus lambda plus x1 plus x2 plus a, lambda x1 plus x3 plus x3 plus y1, and so on. We can just use computer, and we can compute the p plus q or p plus p. And this is, I put the title operation in binary field. It means if our elliptic curve is over binary field. And if our elliptic curve over prime field, you have different formula, but basically you can compute everything with a computer. And finally, we only consider the finite field that we use. As you can see, here, for example, when we try to compute XR, this is lambda square plus xp minus xq. Lambda is compute 3xp square plus a over 2yp. And finally, what you need is the operation on the field. So in order to master in elliptic curve cryptography, you have to really master in finite field, operation in finite field. And for the encryption, we have this algorithm where this is for elliptic curve cryptography over prime field FP. You have for the input as prime P, elliptic curve E, point P of order N, private key, and plaintext M. And then after the encryption, we will get the ciphertext C1, C2, and this is the algorithm. You need to compute Q, and then M become a point M, and you compute C1, which is K times P, and then you compute C2, which is M plus KQ, and you send C1, C2. And to get the message, so we compute M, which is C2 minus DC1. Let's check if M is C2 plus DC1, but D was, D times P was Q, and KP is C1. So we can change this with KP, and C2 is M plus KQ, and you have this commutative KDP equal the KP, and you get M back here. So by computing C2 minus DC1, you get the M. But once again, like I said, this is all depend on our knowledge on the finite field, and I mean to compute, for example, to compute d times p, p plus p plus p plus p, d times, you need that knowledge on finite field. And for the cryptography itself, it's based on the so-called discrete logarithm problem. And so if we know the points P and Q, where Q is K times P, find the value of K. What funny is I have a colleague and she said, okay, you can get P equal 1 over K times Q. And then, no, this is not a number. If Q equal K times P, P is not 1 over K times Q. No, that's impossible. So that's what makes elliptic curve cryptography become hard, is how to find this K. Because once you know the K or the D is the private key, then you can get the message that you want. Okay, so if we are talking about research in elliptic curve cryptography, there are many areas to explore. One of them is for the field operation. There is so-called polynomial basis, optimal normal basis, and then we can, if you are so algebraist, maybe you can play with this basis and a normal basis, a polynomial basis. And if you are more in hardware, software, you can try to make the curve operation faster or more secure and so on. And even for saying embedding a message become a point, that's also one of research. And the research that we have done so far, there is this ECC over prime field, ECC over binary field, and ECC over composite field. We also done the polar throw attack and then try some curve for instant messaging. You know, instant messaging, who among you doesn't use WhatsApp? And you see in the WhatsApp, sometimes it's called end-to-end encryption. That's it. Okay, so then I will explain that later. And also, elliptic curve also used in cryptocurrency. Okay, let me talk a little bit about the field that, like I'm saying before, that you need to know more about how to operate in this field. So in binary field, it means a field that is in the form f to power k, or gf to power k, or gf2, gf4, gf8, and gf32, and so on. So it's a finite field of order 2 power k. And it has representation polynomial basis. So usually it will be in the form like polynomial. If 2 power n means it's a polynomial with order at most n minus 1. And maybe I should write some. Can I write in this whiteboard? Because I'm also supposed to give you any problem that you should solve, so maybe I can explain a little bit about finite field and then give you homework later. So I will give you an example on the finite field GF2 power 3. And Yeah, okay, thank you. So the elements will be, okay, mathematically this is F2x over the ideal generated by some irreducible polynomial. Okay, let me choose an irreducible polynomial, this one. This is 3, so the degree of the irreducible polynomial is 2. And you can change with x, sorry, now I confused, no, x3. This is 3, so this is 3, x cubed plus x squared plus 1. This is irreducible, so this is an irreducible polynomial, so that this is a maximal ideal, and so this ring over maximal ideal, this is field. Okay, so you see the application of algebraic structure that you learn. It's not for nothing. Now it's useful, and you're proud. Okay, so anyway, so this will be in this form: a0 plus a1 x plus a2 x squared, where ai is in F2. So, yes, so we can also write it down 0, 1, x squared, and then x plus 1, and then x squared plus 1, and then who else? X squared plus x plus 1, and 1, 2, 3, 4, 5, 6, 7, one more, x squared plus x. And the engineering people like to write it like this: 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 1. No, I forgot. Okay, so 1, 0, 1, 1, 1, 1, and 1, 1, 0. For the addition, it's easy. You just add like adding polynomials. But be careful when you do the multiplication. This is a field, this is a ring. You can multiply 1, 0, 1 and 1, 0, 1, 1. And this is not 0, 1, 0. Okay, that's something that engineering people cannot understand. Okay, so when you need to compute this, so you return it to the polynomial x plus 1, and this become x squared plus x, and no, still x squared plus x. This is, what is this? 0, 1, no, 0, 0, 0, 1, 1, 0. Okay? And if you get something that, for example, x cubed times x cubed, you get x4, and then you have to divide with this, and you get the, so modulo x cubed plus x plus 1, and this is easy homework for you to say what will be this. And as if we return here, can you see this and this? Okay. If we return here, you remember that when we see how to do this computation with this elliptic curve, so what you will need here is to compute the inverse. And that is not as easy as we did here. Here I give you example how to make the addition and the multiplication, but then for the inversion it's different. Okay, this is called the polynomial representation of GF23. So the polynomial basis is 1x and x squared. And you can also have so-called normal basis. Don't ask me why they call it normal. For me, this is not normal. So, because it's in this form x squared and x 4, where if we put how to say? Oh yes, it's your homework to say what this x for. Okay. Anyway, so this is the normal basis, and you have learned from linear algebra that from one basis to another basis you can have a conversion by using a matrix. Okay. See, linear algebra is so useful. Okay. Let me go back here. Because I'm an algebraist, so I start with this operation with polynomial basis and normal basis. And here, let's say this B is a representation in in one basis, and A is another representation in another basis, say B for polynomial basis and the other one for normal basis. And then from conversion from one basis to another basis, you can use a matrix. Okay, I think I skipped something. Okay. Now, why the normal basis is important? Because as you see, if you write the W is a linear combination of alpha, let me think, 1 plus alpha power 2, and then plus alpha power 4, and so on. And so this is in the form of normal basis, because it's in the form x squared, x4, and so on. And when you make the square of W, when you compute W squared, let's say S is the function that sends W to W squared. So W squared is SW, and then W is this linear combination, and then S can be put in here. And when you make a quadrat of this alpha power 2 power I, this will become alpha power 2 plus I plus 1. And you write it down again, become bi minus 1 alpha 2 power I. It means when you make the square of this, it becomes the previous coefficient. So for example, when W is 10110101, then you can easily compute W squared by putting this one here and become 1011010, and then you compute power 4, put this 0 here, 011011011, and then you can play around until W power 32 and so on. So that's the importance of normal basis, and since the squaring is so easy in normal basis, so we try to do this conversion. But the problem is the matrix M can be very big. In my example here, the base is only 3. But it can be, if we say GF2 power n can be 1,000, and then you have 1,000 times 1,000 matrix. So for the solution, we have this research that we make this storage efficient conversion algorithm, which is basically not using the whole matrix, but maybe only one particular row of that matrix. So it means for the storage, it's not so big. And so this is the algorithm. So for example, from W is 1 plus A squared, and after the conversion, we get in the form of normal basis like this. Oh, sorry, okay. This is the form of normal basis. And for return it back to form of polynomial basis, we use the other algorithm. And this has been improved, and we have also generalized to characteristic tree and also to composite field. But then I try to play with something else. So I have many things to play with that I share with you today. So after this normal and polynomial basis, we try to use a composite field. What is a composite field? So now we can make it bigger. Let's say GF 2 power 12. But now I want also to use composite field, say to 3 power 4. What does this mean? It means this is like before, 2 power 3 means this is A0 plus A1x plus A2x squared plus A3x cubed. But then the AI, can you guess where AI will be? AI is in GF 2 power 3. So now the coefficient also big. It will be so confusing to write it down, but anyway, okay, let's try. Say AI is A1I plus A2I y plus A3I y squared. Okay? You imagine? So this coefficient also polynomials. Okay? And these two fields, they are isomorphic. And we can also have a conversion from this one to this one and return it back. And what we use, so my example there, GF 2 power 12, but we have used is GF 2 power 299, which is GF 2 power 13 power 23. So in the picture, will be like this. Instead of you have this long until 299, you have not so long, still long, 23. But then for each coefficient, you have 13, 13, 13, 13, 13. Okay? So it's not that long, but still long, but shorter. But then it's quite fat. Okay? And we have tried to define the multiplier, give algorithms using LUT means lookup table, and then there is an algorithm, Karatsuba-Hoffman algorithm. And this is for the lookup table, it's like we have this putting like cyclic group, and then you have 0, G power 1 until G power 0 until G power n, and you use this lookup table to compute if G times, what is G times 5, G times 6, and so on. And using this lookup table, it should be easy to compute, for example, G power 9 times G power 11, and so on. And so the lookup table is used for the operation which is inside, I mean the operation which is here. And we use another algorithm for the operation for the GF23. So this is the work with my colleague from electrical engineering, and she designed all this multiplier and so on. Okay. So this is our works using composite field. Okay, let me tell you about something else. So this is like a long history of my life. Started in 2007 when I start with the polynomial basis, normal basis, and then I continue with composite field. And then in 2012, I started with trying the attack. The attack means how to compute K if Q equal Kp, and how to get the K. And one of the attack is called Polatro attack, and we aim to find K. And first we divide G. G is the point on the elliptic curve, the set of points, and we divide G into three sets: S1, S2, and S3. And then we use this algorithm. Start R0 is the point P, and then if P is in S1, and then you take the second R1 become P plus R1, or if P is in S2, and then 2 times P, and so on. So you build this sequence of points from R0, R1, R2, R3, and so on. And because this is a finite group, so the point will meet like this. You start with R0, R1, R2, and so on, and one day, not so long, I hope, the point will come back to, so you will have the point, you will meet the point again. And when you have this point, say Rm equal R2m, and then you can compute the K with this formula. So if Rm is Smp plus Tm, if Rm is this one, Ri is Sip plus Tik, and then you can compute K with this formula. But as mathematician, of course, we're not satisfied with this. We try to use any algebraic things that we can. And what we did is using so-called automorphism. And if that bracket P denotes the subgroup generated by P, and then psi is a group automorphism. If it is in order T, and then we define a relation on that subgroup where R1 is equivalent to R2 if and only if R1 in the form of psi power j of R2. Then we can get these equivalence classes, and with using that equivalent classes, we get a so-called modified polar row. And for the psi, we have used the negation map and Frobenius map, and the Frobenius map means from XY here, you get x squared and y squared. And then you can combine the previous research that we did normal basis. Remember, squaring is easy with normal basis, and this is squaring, and so on. And so we try with small n. This is, I think, n is equal 7 for GF to power 7. And here we need 8 iterations to get that R3 is equal to R8. And then it means 3p plus 1q equal 8p plus 8q, and then you get this, and modulo 71. 71 is the order of p, and you get k that you want. But this is the original Porlatro. If you do compute the equivalent classes like I said before, then you can get that the iteration, so before we need like 8 iterations, and now only need 4 iterations, but compute these equivalent classes is not an easy task either. And I think this one use n equal 13. And we also tried with different n from 7, 9, 11, 13, 17, 19, 23, and 41. And we also try another algorithm, so-called branch cycle algorithm. And we can compare that by using Frobenius. We can have the time is the same, but for the iteration is less, much less, from 30 to 6, 51, 25. This is without Frobenius, this is with Frobenius. Okay. And then I want to try something more. With the finite field done, composite field, and then try the attack, and then what else can I try? The next one, I try this. How about the encryption? We haven't talked about the encryption or decryption. And we tried this elliptic curve integrated in encryption scheme. And the advantage on this scheme is that the message is encrypted to be an element in the binary field. So it will be easier to operate. And what else can we do? Like I said before, I'm interested in this text secure, instant messaging, WhatsApp. Why? Because then I can say my algebra is useful. Then I can say that linear algebra is useful for cryptography, and what is cryptography is useful? That's for us to chat, to send message to each other, and so on. And the interesting use of elliptic curve here is it's used the prime field FP, where the prime number P is 2 power 255 minus 19. And then I challenged my student Januar, okay, let's see if we can understand what is inside this. It's called elliptic curve 25519 because it's used the prime field FP, where P is 2 power 255 minus 19. And we are so motivated by by that because it is implemented for instant messaging. But then he became disappointed because he said, oh, it's only used for key exchange. And for the encryption, it used the AES. Okay, then let's not get disappointed. How if we try to use the previous research, the ECIES, to this curve EC25519. So we tried that, and okay, there's something I need to tell you. So for this curve 25519, it doesn't use the form where it starts from, like I said before, the y square equal x cubed plus ax plus b, or the other one for binary field. So here it uses the Montgomery form, which is defined like that. And its advantage is it is possible to operate without the y coordinate. And so in the text secure application, the curve 25519 is used for key exchange and authentication. However, in this research, we show that it can also be implemented in simplified elliptic curve integrated encryption scheme. And so this is my new game, but I put it 2019 as the end because I don't know after this what I will do later on, because after lunch I will explain something else, my other games on coding theory. And so this is also joint work with the School of Electrical Engineering in ITB. And okay, this can also be interesting to explain to non-mathematician because it uses money. And what is Bitcoin? So cryptocurrency is electronic money or virtual currency. Well, everybody maybe use Grab, Gojek, OVO, and you get discount with the electronic money that you have on your application. So even though you don't use Bitcoin, but sort of Bitcoin you use every day. So as you can see, algebra is everywhere. Not only your password, also your WhatsApp, also your OVO application, Grab or Gojek or Uber and so on. And Bitcoin is the biggest successful representation of the cryptocurrency. And payments are recorded in public ledger using its own unit of account, Bitcoin. And it is in the form digital currency created and held electronically. It can be used to buy things electronically, and in that sense, it is no different than conventional dollars, but different from the credit card or anything else that you've been using. This Bitcoin, it has no authority. So if you use your credit card, you have the bank as your authority, but for Bitcoin cryptocurrency, it has no authority. But let me talk about how elliptic curve fit inside. So the elliptic curve used in this Bitcoin is the digital signature. And Bitcoin uses the digital signature to prove that signature owner is the account owner. In other words, owner owns the private key. And then private key is used to create signature, and public key is used to verify the signature. So it's like you have your credit card, you pay for your hotel, and then you sign it, and then with elliptic curve, the digital signature algorithm, we try to authenticate that signature. And it used another different elliptic curve, which also a big prime number p. And it's not as easy to saying the before 2 power 255 minus 19. This is longer. 2, 2, 5, 6, 2, 3, 2, 2, 9, 2, 8, 2, 7, 2, 6. Okay, just believe me, it is a prime number. Okay, so the curve is y square equal x cubed plus 7, where if we want to draw it, it's easy, I mean, in the real field. And this is the scheme of elliptic curve digital signature algorithm. This is for the signature generation, and this is for the signature verification. And then, of course, when you do research, you try to find something new. So we found this scheme called group signature, and how if we put it in that curve, I don't know what's its name again, SECP256K1. And we try to implement that group signature scheme to this curve. And so for this group signature, it means that there is a group of people that can verify instead of only one person. So this is our recent research, and we implement the group signature on this transaction using cryptocurrency. But then, well, Rudy has asked me if I still doing the elliptic curve cryptography or not. There is this also story about quantum cryptography, where if we have quantum computer and then everything related with RSA, ECC maybe not so secure anymore. So then I met Fred, and he suggested to do this code-based cryptography that combine the coding theory and cryptography. And there is this scheme, McAleese cryptography, which is based on coding theory, and there is construction of secret key using matrix G, S, and P, and then construction of public key, and then there is this coding theory involved where for the encoding and decoding. And we just started from 2017 still now, and we want to explore the use of skew cyclic codes and other codes overing that I will explain this afternoon. Another alternative is so-called supersingular isogeny Diffie-Hellman, where here what we exchange is not the point on the curve, but we exchange the curve. So from one curve E, we make the curve EA, and then from EA we make the curve EAB, and then Bob can from E making the curve EB, and then making the curve EBA, and then EBA and EAB become the same curve, isomorphic. Anyway, so this is not based on the discrete logarithm problem anymore, that maybe it will be secure for the attack from quantum cryptography. So this is the source. I'm taking this from Michel Watt-Smith's slide when he did this SIM school on numbers, matrices, and graph in ITB 6 years ago, and I also use Bitcoin introduction by Jalal Rohani. Thank you very much. Any question? Well, on time for lunch. Okay, if yeah, okay. Well, I haven't prepared anything for homework yet, so maybe I will give you the homework on Friday and you return it back to me next week. Homework during weekend. And if there is no question, we will meet again after lunch and I will talk about something else, which is coding theory. Thank you.
Thank you, Dr. Intan, for the presentation. Please give applause to Dr. Intan. Okay, this is the end of second session, and before it, I will give an announcement. Dear participants, on Saturday, you are all invited to have an excursion to some interesting place in Yogyakarta. The places are Museum Sandi, so Jiwan Temple, Banyu Nibo, and so on. And this excursion is free, no need to pay additional fee. And for you who want to join it, can register your name at the front desk. And the registration will be closed on Thursday, 18 July. So the next agenda is lunch, and you have 1 hour and 30 minutes for lunch. As the consequence of this additional time, the schedule will be at 2:30 minutes. So you can lunch, and the third session will be held in 2 p.m. You have yeah. So you can lunch now at University Club. The session in 2 p.m.